Iya, masuk. Oke, oke.
Ini udah jam
2 jam nggak sih, Pak?
2 jam itu.
Oh, jam 3. Udah ya? Udah ya?
Ini, nah ini kalau mau pakai.
Iya.
Kalau ada kan.
Kedengeran. Sebenarnya sih ada audiens itu, cuma kan
Ya.
ya.
Jadi kalau pakai
Screen share aja berarti ya? Screen share aja berarti ya?
boleh screen aja. Tapi
ini ya?
kalau misalnya kamera itu nggak bisa dilihat sih kan? Di streaming gitu.
Sorry. Oh iya, ini. Ini kamera dari mana?
Kamera sih cuma.
Tapi kurang berapa? Menurut saya yang kelihatan nih. Mundurin aja ya.
Mau saya gerak-gerakin ya. Kalau itu. Kalau mundurin itu.
Mundur.
Ya.
Ini.
Ya kan?
Ya. Dia secara dapat sini kan.
Tapi nggak mau mundurin dikit. Mundurin. Oke. Sama ini, stage kalau misalnya saya mau switch dari slide ke di sini. Gimana? Di kamera tak kelihatan. Mau balik lagi. Support. Oke. Kalau mau di slide.
Screen share aja ya.
Oh ya. Tunggu. Kalau gitu saya keluarin dulu deh. Mana tadi ya? Sini ya. Ini saya jadi di sini lagi. Coba itu gimana tadi?
Show.
Oh ini ya.
Gitu ya.
Ini udah.
Saya lagi. Oh, ke bawah kali ya. Nah.
Bingung kan? Gitu ya. Tapi di kamera kan di streaming tadi belum ya? Ini bukan sini.
Gitu.
Gimana caranya?
Pengennya ke sini ya? Ke.
Nggak apa-apa juga sih.
Udah.
Ya.
Kelihatan dulu. Dikecilin aja kali ya.
Apanya? Ya boleh. Kalau di bawah aja. Oke, gitu aja. Oke, Oke, good afternoon everyone. Assalamualaikum warahmatullahi wabarakatuh. So, well, this is the screen from last time, yeah. I mean the slides from last time. So, how are you? We finally met offline. Yesterday I heard some of you we're having final project in astrophysics. Who are how many of you, if I may call on? Sorry, you need. But then who else? You need. Asif. Iqbal. So three of you. May I know what kind of project in astrophysics? Bus? Oh, okay. Okay. Uh, spectroscopy analysis. Oh, super giant. Okay. And then neutron in galaxy cluster. Okay. Okay, interesting. So how does the what do you call it? The arrangement in UM? You have to submit final project in order to graduate, or is it just a part of the course? Okay. So there is no like an undergraduate thesis. Oh, there is an undergraduate thesis. Oh, that's the final. So it's not part of like the course of like astrophysics. No, this is the final project. Um, so how deep should you go? I mean, is it publishable, or is it like for proceedings something? Depends. Depends on the professor. Okay. I see. Yeah, I mean that happens here too. Yes, yes. Okay. Well, sorry, I'm asking for those who are working in astrophysics because I myself is working on that too. So, in order to do final project in astrophysics, what kind of tensor? Okay, Einstein's field equation. You do like Einstein's field equation? Okay. Oh, is it a compulsory course? Not so not every one of you takes it. Okay, not everybody. So it's like elective. I see. Okay. Well, yeah. I'm asking because maybe for those who are taking the cosmology, my course will be a bit boring. Will be a bit elementary. But well, I hope it helps it. Yeah, as I said, actually, uh, well, yeah, I mean, my research interest is in physics, and I've been doing like all quite a while. But then when the department offered me this to teach this course, I was swamped with other projects, and then I think for 2 days it's kind of like hard to give a course in cosmology in astrophysics. So I think I may do something less advanced. Okay. All right. Before we start, any question from all of you? Please do. Okay, can you see? So for this second part, I may rely more on the whiteboard, yeah, glassboard. I don't have much many slides to show. Yeah, I don't have many slides to show for the second class, so I will do many derivations. Well, I go. What time does this class end? Yeah, actually, and then do you have other? Wow, it's quite quite condensed. Well, so you must be exhausted, all of you. All right, so if there's no question, let me just start. So last time we were in the yeah. So yeah, last time I talked about the Gauss principle of least constraint. Well, maybe I should go back a little bit uh, about constraint. Yeah, you all know constraint, and constraint can be in general classified into holonomic and non-holonomic. What we are mostly talking in this section, and also in many areas of physics and engineering, uh, is that the constraint in the form of equality, yeah, be it holonomic or non-holonomic. As long as it's in equality like this, it can always be. I mean, I'm not saying it's easy to solve, but it can always be done. So yeah, non-holonomic, it's either the constraint stated in inequality or inequality, but non-integrable. What I mean by non-integrable is that the constraint cannot be brought. So in general, we can write down the constraint like this, and it cannot be brought over this one. So you cannot find any function f whose total differential gives you this pressure. That's what I mean by non-integrable. And sadly, or maybe fortunately, depends on your philosophy. Either you are optimist or pessimist. In nature, most constraints are non-integrable. Well, not only in nature, but in engineering as well. Yeah, most constraints are non-integrable. So last time I talked about uh, the Gauss principle of least constraint. Yeah, the Gauss principle of least constraint actually takes into account the non-holonomic one. So the constraint here is general. It can be holonomic or it can be non-holonomic as long as it's in the form of equality. Yeah. So what this principle actually says that the true equation of motion in nature or in the system, say, with constraints is the one that minimizes this Gaussian scalar function. Okay. Let me rephrase it. The correct equation of motion have to add compatible with the given constraint. So the equation, the system is equipped by some constraints. So the Gaussian function, the minimum of the Gaussian function gives you the equation of motion. If the constraints are zero, there's no constraint, then the minimum is achieved when we get the ordinary or the usual Newton's equation. But when when constraint is present, then the situation is a bit more tricky. yeah, we discussed about this, and then I think last time I talked about the Udwadiya-Kalaba fundamental equations, yeah, where they try to give a general solution for uh, the constraint system, the equation of motion for the constraint system. So yeah, this is the in general way when I take the derivative with respect to time, I have this second order equation, and don't forget that a JI is a, a matrix, m times n matrix, yeah. Uh, so the matrix here needs not to be square. Okay, can be any general matrix. So sorry, this maybe I should put it. What should I put? Okay, let's put it like this. Okay. Right. Oh, sorry. H times 3n. H is the number of constraints. 3n is the configuration space. So last time the claim was that the general equation of motion can be given by this, while the what is it called? The generalized inverse, the plus sign that indicates the generalized inverse or the Moore-Penrose inverse. Okay, I think I prove this thing, yeah. Oh yeah, by the way, I also shared this with Dr. Anawati. Have you got the slides here? Maybe she will, or sorry, with the committee, with Dr. Anawati and also Dr. Arohim. Maybe they will share the slides later. So I mean, you can have the slides. I shared with them, and so yeah, I shared with you basically. Okay. Anyway, with this, I proved that the good one yang Kalaba is the correct equation of motion consistent with the constraint of the system. So I think here where we ended last time. So any question regarding this? Sini kosong. Okay. All right. So well, we know that the Gauss principle of risk constraint is a nice principle, but it's kind of like complicated because it deals with vector. Yeah. Well, you know, you in classical have you written about the D'Alembert principle? No. Okay. Maybe I'll talk about that. So of course, in analytical dynamics, there are several what do you call this? Optimization principle, right? All of them actually lead to the same equation of motion. I mean, the basic equation of motion is we know that Newton's equation of motion, but then people, or rather mathematicians and scientists from the 17th to 18th century devised method to obtain equation of motion from alternative paths or alternative methods. So Gauss principle is one of them. Yeah. Now I'm going to talk about D'Alembert principle and also principle of virtual work. But before that, I'm going to talk about generalized coordinates. Well, let's take a look at this very simple phenomenon and simple values of disorder. I don't know how to. Can I make it? Okay, so it's basically a simple pendulum. Well, we know what happens here, and we know the equation here. The mathematical equations and is given by Newton's laws. Yeah. Since it is motion into dimension, then we have two equations for x, motion in x coordinate, and motion in y coordinates. Right. That's what happens when you don't have constraint. When we impose constraint, the equation becomes a bit, well, when we impose constraint, sorry, I'm not saying when we impose constraint. Actually, the system itself is constrained. Yeah. This is a two-dimensional motion, but actually the constraint is implied. What is the constraint? The constraint is just that the length of the pendulum is fixed. So there is no more independence between x and y. We have two degrees of freedom, but then both is constrained. So effectively, we only have 1 degree of freedom. So by choosing a smart choice, which is picking or transforming from Cartesian to polar coordinate, we can express the two equations, the two Cartesian equation into this one, and these two can be eliminated. We can have only one single equation, and this is the already familiar equation that you know, right? The simple pendulum equation. Okay, basically what I was doing here, what I was doing is that I start with original coordinates. There are 2 degrees of freedom, and then the constraint makes the 2 degrees of freedom reduces to 1 degree of freedom, and that's where we transform or we pick smart choice, which is a polar coordinate. In this coordinate, the equation of motion is simplified. So this is what I mean by an example of generalized coordinates. Okay. So in general, if we have n particle system, then we have 3 n dimensional configuration space, as we talked earlier, right? Or 3 n degrees of freedom. So if we have m number of constraints, then the DOF is reduced to 3n minus m, right? So this is the original coordinate. I run from 1 to n. Now I can define what we call the generalized coordinates. Q of j runs from 1 to the effective number of independent degrees of freedom. Now, well, using simple, and I can take a total differential. I get this one, right? Using simple calculus. And remember that we also have the word, the definition of word, yeah. And so, using the definition of word, I can define that the word is given as some generalized form working on generalized coordinate. Remember, this is the work expressed in the original coordinate. Now, I can also express the work in terms of the generalized coordinates. And since the work is scalar, so it must be scalar in every in all expression. So this is also scalar. And the work, we know that the dimension of the work, right? So it should stay. The dimension should be the same, right? This is the dimension is 4 times displacement, right? So here the dimension should also be the same. But now we don't have original, or we don't have the ordinary displacement. We have generalized displacement. And generalized displacement, it doesn't have to have the same dimension as the ordinary displacement, right? Like for example, in the previous example, the original displacement is x and y, and these have dimensions of length. When we pick the generalized coordinate, pick theta, and theta, what is the dimension of theta? What is the dimension of theta? Dimensionless. There is no dimension. The unit is in radian. The dimension is, it has no dimension. So when we want to express the work in terms of generalized coordinates, so there's possibility that this is dimensionless. So now the generalized is abstract. That's what I call the generalized force. The generalized force needs not to be in the same dimension as the ordinary force, but the product of them should give you the same dimension as work. So that's how it works. Okay. Now, well, that's when I go to the principle of virtual work. All right. So here I can define what I call the virtual displacement. Okay, the virtual displacement. What is it? What is virtual displacement? So it is an imagined displacement. So this displacement doesn't really take place. Okay. Sorry. Question? So this displacement doesn't really take place. Or you can imagine that this takes place, but in an instant time. Okay. So there is no time difference before and after the displacement takes place. In other words, this doesn't really happen. Okay. But this displacement is consistent with all the constraints imposed. So, for example, if I have a particle being on this curve, suppose that this is only two-dimensional, yeah. The system is two-dimensional, x and y. We have a particle of mass m sliding on the curve. So what would be a possible virtual displacement that I can have? Well, you can imagine any displacement, but one thing that is consistent with the constraint. What the constraint, we know that since it is required to slide on the curve on this cable, let's say, yeah, then the only virtual displacement or displacement that you can imagine happen, and is consistent with the concept, is like this: delta R. Delta R can be decomposed into delta X and Y. Okay, so I'm writing this virtual displacement with delta to distinguish it from the actual displacement. So actual displacement, I'm using dr. Now the virtual displacement is delta R. What is the difference between dr and delta R? In delta R, there is no, so the dt is 0. Okay, that's the only difference. In dr, you may have dt non-zero, but in delta R, there is no time difference, or in other words, it happens at instant time. So this is another illustration. If you have three-dimensional system like this, and for example, you have a ball or a point particle rolling on a hemisphere, for example, like this. Since it is required to roll on a hemisphere, not off the hemisphere, then the constraint is that this ball should only move around this two-dimensional surface, right? So the possible virtual displacement is that along the x and y, okay, something like this. Sorry, this is not. This doesn't look too clear it. Okay, right. Oh, and then we also have, let me remind you, one, one, sorry, question? The question? Okay. Yeah, this last week I said that in most cases the constraint force does no work. Yeah, the constraint force. Why does it does no work? Because it is always perpendicular or orthogonal to the displacement, right? The constraint force is always perpendicular to the displacement, so that's why it doesn't do any work. Now we can use that result. We can use that result in our discussion here. Okay, so that equilibrium, this one, right? What I mean by static equilibrium is that we have a system that does not move, or the acceleration is zero, right? So this is a static system, static case. So obviously this one holds, right? Now, if I can partition the force into the external and the constraint force, we know that the constraint forces do not work, right? So uh, the only component of the force here is the external force. So that means that the sum of all external forces dotted with the delta r, or the virtual displacement, is zero. What is this? This is the definition of work, but since the displacement is the virtual displacement, this is what we call the virtual work. So this is the virtual work. So this leads us to what we call the virtual work principle. Says that in static equilibrium, the total work done along the virtual displacements is zero. Okay. Well, it looks simple, but it has a very significant application. It has many significant impacts in science as well as in engineering. Any question? Okay. Right. So, well, this is not a really new principle. Actually, principle of virtual work is actually an old principle. Yeah. I think the first one who proposed it was Archimedes, but he didn't call it principle of virtual work. Obviously, he called it principle of the labor. So basically, this is the widely used principle in structural engineering or in the aeronautical engineering. Yeah, when you want to design a stable structure or you want to design a stable structure as well for the planes, then this is the widely known, the widely used principle. But think it's running out of battery. Let me. Okay. Let me just skip this. So this brings us to D'Alembert principle. So principle of virtual work. This is a very powerful principle, but it only works for the what do you call the? It works only for the static system, right? Well, in physics, we mostly deal with dynamic systems, so I think we should extend or we should modify the principle, and that's what D'Alembert did, and this is what we call the D'Alembert principle. Well, the idea was simple. Here was that we just extend the principle of virtual work to include the rate change of momentum or the rate of the acceleration. That's it. Plug in here. And so what was to be the principle of virtual works now becomes something like this. Okay. Well, this is actually what we call the D'Alembert principle. This is nothing but Newton's law, Newton's equation. And we can solve problems with this. But actually, the power of the D'Alembert principle doesn't lie here, because the equation in this original sense is really not helpful. This is just Newton's equation written in some peculiar form. Okay, so how can we make use of the D'Alembert principle? Well, actually, this is what I'm going to start writing down. But before, any questions about this? So let me just the question. I think I'm done with the slides. I can start work writing down. Let me just stop sharing. Okay. This is the later. Okay. Is it? Look, doesn't look. Okay. This was from the previous one. Do you prefer writing here or? Sorry. in a smart device? Okay. I mean, let me just. Do you prefer black or white? Sorry. How to turn it to white? Oh. What? No, I mean, you want the various people that can like the background before. Okay, thank you. Thank you. Great. All right. What happens if I screen share? Okay. So basically, this is the number of degrees of freedom, the original number of degrees of freedom. Let's call it 10. Well, this is the number of totally 3. Number of constraints. I'm going to call the effective degrees of freedom as n. N is 3 capital N minus k. So basically, my generalized coordinate will run from 1 to n, small n. It is in general a function of just write down like this. It's Q1, Q2, up to Q small n. Okay. So, well, Q in general is a function of with entities. Sorry, it's a function of R. And so is the other way around. R in general is a function of and time. Okay. So now I want to calculate the velocity. The velocity is simply the derivative of Ri with respect to t, right? But now, okay, I must also include this. Now, R is a function of Q and T in general, and Q is also a function of T. So how does this work? Well, we have to write down like this. We have Q, let me use Qj, and this is the Qj dt, right? Plus the derivative of Ri with respect to t in partial. So this is the total derivative, this is the partial derivative. So the summation comes from, okay, maybe I'm not using J. I'm using K. Let's say K. So this is K T. K here. Okay. Right. So and also I'm talking about the, is it too thin or we can on the other hand, little bit. It's better or worse? It's worse. Okay, it's okay. We have the virtual displacement. Okay, so this is the displacement. The virtual displacement is just delta. Okay. Thanks. Let me use J instead of K. I'm going to use K as well. Delta Q K. Now, so what do we need? Okay, remember that the Dallas-Ford principle says that Dallas-Ford principle says that the summation of I forget. Summation of all forces minus P dot. This is dot product with delta Ri. This is 0. Okay, so this is the Dallenberg principle. Now, okay, so we need to find each term, right? So let's do the first term. The first term is Fi dot delta Ri. Okay, this can be written as the remember that I can change it into a generalized force. Yeah. So this one, the whole thing, right? Okay, now I can write down like this. I have an I dot I can times down the Q, not those the G. Down the Q J. So the summation of them all, I, and I can switch the summation. I can switch the summation. I can write down like this. This is just the summation of J, the summation with respect, summation J of what? Of, we call it Fj times delta Q J. And F script J is this is F script J. This is just the, what do you call the generalized force. So this is the Fi dot. Okay. So this is from the first term. First term here is one, as we know. Now, how about the second? Well, the second term can be second term can be written or elaborated like this. So what is the second term? We have use this one. Sum of pi dot delta r. So we want to know what this is. We want to calculate what is this. So this is just the same as if I'm, we know that pi is the momentum of the ith particle. The momentum is given by the mi times ri dot. So the momentum dot means that this is the ri double dot, right? As simple as that. Assuming that the mass is constant. But now I can write down this as that one. So this J here, I have J delta QJ, right? So we just pull all the summations outside. I have sum over I, sum over J. I can also put the MI here, and then the vectors being dot product are the RI double dot with partial RI, partial QJ. And this is multiplied by delta QJ. Questions? All right, maybe right down here, but maybe I'm just gonna use the space here. So This is the, basically I can write down like this. So Ri double dot, this is just the, right? So Ri double dot something will be written as the d of Ri dot dt dot partial Ri dqj. Now I can use the Leibniz rule to write down like this. This is the d of dt, ddt of Ri dot partial Ri partial qj, right? Minus Ri dot dt of partial Ri partial qj, right? So I'm using this rule. Okay, this is just Leibniz rule, yeah. I can put everything here. So I have let me just write down here. Find sum of I, sum of j of mi. Okay, this is multiplied by this whole thing. Yeah. D dt. Let me just find on there so that it doesn't. Okay. So let me just mark here. Right. Pi dot dot delta I, sum of I. This can be written as the summation of I, summation of j, mi. Now this is the d dt of Ri dot partial Ri partial qj minus Ri dot d dt of partial Ri partial qj multiplied by delta delta qj multiplied by delta qj. Okay. Not too long. Question? No? Any question? Okay. We just bring up this part. I think I erased what I was, what I want to, what I want to write down. So I'm just writing down again. So this is the one that I erased. This can be written like this: summation of k. This is the qk, and this is just the qk dot. Right? The qk dot means that is the dqk dt plus. Okay, this is the one that I want to state. Right. So now, all right, I'm going to each term, right? And it's a calculate each term. So let me just erase it here. Q. Let me call this the first term as term 1. This is term 2. Right. Okay, let's just take this term. I have B of I like this. So I want to calculate well, B of I. This is just I dot there. B of I, the velocity is just I dot. So if I want to calculate, what do I want to calculate? I want to calculate partial BI partial Q J dot. Okay, remember that B of I is a function of Q dot, right? So if I want to take the derivative of B of I with Q J of dot Q of J dot, what do I have? This function derivative works on the first term only. Okay. The second term doesn't contain Q dot, so only the first term is affected. So what I get, this is just the summation of unwanted goodness. So you see, okay, let me just write down slowly. So this is, I'm taking the derivative with respect to Qj dot of what? Of the summation K. I, UK, Q, K dot, right? Since this coefficient doesn't contain Q dot, it Q dot only here. So what we have is just so I have partial of QK dot partial QJ dot. What is this? Anyone knows? What's the result? This is just Kronecker delta. Kronecker delta of KJ or JK. Say. And so the Kronecker delta makes all the summation collapses. Yeah, sorry. It makes all the summation collapse unless when K is equal to J. Right? So the only non-zero term from this summation is when K equals J. Or in other words, we have this is just dr I, oh sorry, partial R of I, partial Q K. Sorry, partial QJ. Partial QJ. Partial Q. So we have this relation. We have this relation. Okay. I'm gonna keep this relation later. Maybe I'm just writing down. I'm gonna write down here the relation that I'm here. J dot. Yeah. This is just, if you look at this relation, it is quite nice. This relates the partial derivative of velocities with its partial derivative of displacement. The left hand side is both velocities. The right hand side, sorry, I don't. I mean, you see, this is not good. This is simply partial uj. We don't know. Okay, the left hand side is velocities, right? Both the numerator and the denominator. On the right hand side, displacement. Okay. So we have this relation there. Okay. What else? Well, if you see this, I can also I also want to calculate the maybe I need to calculate the space. Space here. Now I want to calculate different quantity ddt of partial Ri partial uj. So this is basically how to calculate this one. What is that? Well, this is the total derivative when taking the derivative of this voltage with respect to time through all the dependence of this quantity. Right? So this can be done by this one. Yeah. Let's call it L, sum of L. So this is the derivative with respect to QL. What is this? This is just the partial Ri, partial Qj. And then I'm multiplying it with QL dot. Okay. Plus the partial derivative of this thing with respect to time itself. So the partial derivative of partial Ri partial Uj. Okay, the nice thing about derivative is that the second or higher derivatives are always commutative. Commute. What I mean by commute is that you can always interchange the sequence of the derivative, right? So I can put a partial t inside and partial qj outside, right? So I'm just gonna put it like this. I'm gonna switch the order of the derivative because both are partial derivatives. Right? It only works with different variables. But we know from mathematical physics that partial derivatives commute. So I'm just gonna write down like this. Okay. So the second term can be transformed into that. Not the first term. Well, okay, maybe I'm going to use this one as well. The first term. This is nothing but the second partial derivative as well. Yeah. This is the QL, partial QJ. So both the first and second terms, they contain partial derivative with respect to QJ, right? This and that. So I can pull them out I can put up them out. Uh, now this is the it becomes what does it become? Ah, right. So I'm just going to pull partial uj out because both terms contain that, right? So what is inside the parenthesis is the rest, and the rest is just sum of L partial. Sorry. Wait, sorry. No. Yeah, that's correct. Yeah, partial Ri partial QL multiplied by Q alpha, right? This is from the first term plus partial Ri partial P. This is from the second term. What is this? What is inside the bracket? This is nothing but the one. This is just the definition of V of I, right? This is the definition of V of I. But then we have the relation. We have the relation that d dt partial I partial uj is just the partial vi partial uj. Okay, so this is another result that we can use. And I'm also going to save this result. Question. P of so on partial uj. This is just partial VR, VI, partial uj. All right. So I think we have everything we need to plug into 1 and 2. Yeah. To plug into 1 and 2. So right. Why? Because if you see here, this is the first term here. Here, this is just ddt of v I dot partial ri partial uj, right? And this is the second term. This is just v dot of ddt of partial ri partial uj. Now, we can insert this one. The partial ri partial uj is just the same as this one, right? So okay, let me just split up the whole thing here. we have the dt of vi dot the partial ri partial uj, which is just the partial vi partial uj dot. Okay, this one this is like that. Right. Okay, let's as it is here. Let's take that. Let's not bother with DGT first. Let's consider what this is. You can see this can be written like this. This is just half of what? Of partial uj dot of v squared, right? Of v squared, because v squared is just v dot v, right? This is just v squared. V is a vector, vi is a vector, so if I don't product vi with itself, it gets vi. And this is just the result of this operation, right? And so is the other one. You see here, I can insert the function of I to change with this one once again. Okay. Sorry, no. Let me check it. I get confused. No. Actually, yeah, this is right. Function if what I wanted to write down was actually I can change this into 10. And this one will be changed into partial vi partial uj. Okay. So now I have also rate equation. This is from the first term. Lot of operation from the second is like vi dot partial vi partial uj. If this is partial vi partial uj dot, this is just partial vi partial uj. What is this? Well, we can do the same thing. This is nothing but like this. Right? Okay. So now I'm operating here. It's right down here. So what do I want to calculate actually? This is just the m of I times well, the first term is ddt of what? Of half partial vi squared partial uj. Okay. Or maybe I can just insert m inside directly, right? What I'm saying is that I insert m of I here into here and there directly. So what I get is, well, the first term is ddt of what? Of ddt is open fully bracket. Because I'm gonna get all the brackets I can draw. This is ddt of now I have this one partial uj dot, right? Of what? Of half mi vi squared, right? Okay, I can also insert summation. So I have double summations, right? The summations also commute. I can insert summation I inside. I'm just gonna insert it here. Right. So this is the summation of I of one half m of I v of I squared. All right. Minus the second term. The second term is partial uj of what? Summation of I. I have one half again, right? Mi vi squared. So the difference is just that the first term is with respect to uj dot, second term is with respect to uj. All right. So I close the bracket, multiply them all by delta qj. Right. You can see what's going on here. We know the definition of kinetic energy. Yeah, last time. This is the kinetic energy of one particle is just half of mi vi squared. So here, this is the total kinetic energy, right? I call it T without subscript. This is the total kinetic energy. So, what do I get here? This is just J of what? dt partial T, partial kinetic energy again, partial kinetic energy, partial uj dot minus partial kinetic energy, partial uj. And this is times delta of uj. Okay, I think we can almost see something here. Question? Sorry. All right. So this is from the second term, yeah. From the first term, okay, let me just erase this. Remember that from the first term of the D'Alembert principle, right? The D'Alembert principle, we have D'Alembert principle, we have F I dot, and this we know that already. This gives us the J of F script delta U J. So we can join them together. I'm just writing out here. I have the equation So all of them are sum over J. We have here F of J. This is the generalized force. F of J minus ddt of partial kinetic energy partial Qj dot minus partial kinetic energy partial Qj. Oh, sorry. This is closed. Okay. Right? Okay. This is multiplied by delta Q. I mean, upper delta. Not Q. G. All right. And this is equal to 0. Right? Anyone recognizes what this is? Do you recognize what is inside the bracket? Sorry. Good forward. Well, no, not quite, because we are no longer in static. Okay, let me just write down. Maybe this is not really apparent, but how about I'm writing out like this? Okay, well, how about writing out like this? So since this whole thing should be 0 and delta Qg is arbitrary, then does not imply. This implies that the one in the parenthesis or in the bracket should be 0. We just erase this. And this is what we call the Lagrange equation. So basically, the power of D'Alembert principle is to bring us Lagrange equation. Well, you may recognize this to be some sort of Euler-Lagrange equation. Not quite, but we are close here. This is what we call the Lagrange equation. This is what we call the Lagrange equation. Now, what is F of J? Once again, this is the generalized force. Yeah. The F of J is generalized force. This is the generalized force. And well, it is constructed from the ordinary force. Yeah. If you recall, this is just what is it? Sum of I from I dot partial I partial Qj. Right. And so it is constructed from the ordinary force. So just like ordinary force, we know that the ordinary force can be classified into conservative and non-conservative, right? The force can be conservative and non-conservative. F of I in general can be conservative What is the requirement for being a conservative force? Expanded dependent. In other words, any conservative force can always be written as the gradient of some scalar. The scalar can be identified as the scalar can be identified as what we call the potential energy. Now we have minus here for potential reason. So any conservative force can always be written as the gradient of some potential energy, which is a scalar function. In other words, for any conservative force, we can always define a scalar quantity, which we call the potential energy, and whose gradient gives us the force. And that doesn't happen for non-conservative, right? For non-conservative force, we cannot have this relation. So in general, we can have conservative or non-conservative generalized force, right? Since generalized force can be constructed from either conservative or non-conservative force, ordinary force. I mean. So now this generalized force can be I can write down, yeah, I can, what do you call it? Can be partitioned into what I call the let me just write down like this. This is the Q capital QJ of what the conservative plus capital QJ tilde. The capital QJ tilde is the non-conservative part of the generalized force. The Q, capital Q of J is the conservative part. The capital Q of J tilde is the non-conservative part. Okay. So any generalized force can always be written like. Since I can also define, not define, but I can also write down the conservative force, right? Let's take a look at this Q, capital Q J. This is just the summation of the conservative ordinary force, the product with this one. But now the f of I can be written as minus gradient of some potential energy, right? This one like this. Sorry. Yeah. Right. And this whole thing can be written as, or this is just the definition of what we call the J, Q of small qj, right? This is just the gradient of the potential energy with respect to the generalized coordinate. This is the gradient of potential energy with respect to the ordinary coordinate. This is the gradient of potential energy with respect to the generalized coordinates. So we have minus here, right? So this whole thing can be written as like this. So the generalized force can be written as the minus partial V partial Q J plus the part that cannot be written like this. So I'm just calling it like this. So the conservative part can be brought to the left hand side. The conservative part can be brought to the left hand side. What do we have? We have here. Okay, so I should talk a little bit more about the potential function itself. V is what we call the potential energy. And this potential energy, well, we can assume that the potential energy only depends on the position. Okay, so this depends on Q of J. So it doesn't depend on the velocity or the dot or on the Qj dot. Depends only on the Q of J. In this case, in this condition, the partial derivative of V with respect to the Qj dot is 0. Okay. So we can safely assume that the potential energy is a function of position only, generalized position, I mean, and not on the generalized velocity. So I can bring this to the left hand side. Okay. Let me just write down here. So I have d dt of partial t partial qj dot, yeah, minus, sorry, I close it, minus, now I can join this and that, minus partial qj of what? Of t minus v, right? So what is left on the right hand side is just the non-conservative force. So now I can define another quantity which we call, you all know already, the Lagrangian, right? The Lagrangian. This is just defined to be the difference between kinetic and potential energy. And with this definition, you can call this one as the Lagrangian, right? How about this one? Well, I can also put this one, the Lagrangian. I can put Lagrangian here, right? Since this is the derivative with respect to generalized velocity, and the generalized velocity is only contained in the kinetic energy and not on potential energy, right? I can as well change this without changing everything to be like this. Sorry, J dot of T minus V, right? The second term is 0 anyway, right? The second term is 0 anyway, but I'm putting there in order to express it as like this. So, okay. All in all, I finally came to result. This is what all this Lagrange equation. Lagrange equation is nothing but the famous Euler-Lagrange equation, right? But now, if you recall, we are deriving it from a completely different method. Yeah, we are deriving it from completely different method. And also we have a modification. The right hand side is not 0 here. So remember, if you derive the Euler-Lagrange equation from Hamilton's principle, you have 0 here. Why? Because from this from the beginning, we assume that the system is conservative, right? But it may not be. You can have a non-conservative system. Now, the Lagrange principle actually gives you other Lagrange equation, but with two exceptions. First, it gives you a completely different paradigm, right? Remember, if you start from Hamilton's principle, you start from the initial point and final point, right? You are asked to calculate what is the path between point 1 and point 2, which minimizes the action. That gives you the Euler-Lagrange equation. So this is actually the variation of principle, right? You are given many variations, something like this, right? From this infinitely many possible paths you can choose, there is one that is the correct one. I suppose that the correct one is given by a friend. You are deriving on Lagrange equation from Hamilton's principle. You start from this paradigm, right? So in that sense, Hamilton's principle is what we call the integral principle. You start from the integral, right? You know the where you start and where you end. What you need to find out is the extreme path. But from the number principle, you don't know the final point, right? You start from Newton's law. You start from Newton's law, but then you are doing what we call the virtual displacement, right? You suppose, well, we can imagine there are many or there are infinitely many virtual displacements you can draw, and which one is the correct or which among these virtual displacements give you the correct equation of motion? That's where you start when you do deriving the Lagrange equation from the D'Alembert's principle. Both give you the same result. Okay, right. The second exception is that from Hamilton's principle, as I said, you always assume that the system is conservative. So all forces can be derived from the gradient of any function or any potential energy. Well, it's not always the case. Yeah, from the D'Alembert principle, we can relax that assumption. We can say that, well, the force can be contributed from the conservative factor or the conservative contribution as well as from the non-conservative contribution. The conservative contribution gives you the equation on the left hand side, right? This is exactly the left hand side of the Euler-Lagrange equation. But if you have non-conservative contribution, that will take into account on the right hand side. And in some sense, if you are doing, for example, rigid body, or maybe you are dealing with robotics, yeah, this form is more useful because, for example, in quadcopter or in drone or in robotics, the forces that you use as a control or the forces given are most likely non-conservative. Like, for example, the dissipation force of the air or the force of the wind, we cannot make them conservative, or we cannot derive them from some potential energy. So you cannot dismiss those possibilities. Okay, I think I still have so many things to tell, but I think it's best to stop here. Any question? All right. I hope it's not too trivial for you. Well, if there is no question, I think up here you have like 10 minutes for break before you start another class. Well, thank you very much for your participation. Hopefully, if you are interested in collaborating with me, well, as I said, I'm doing research in astrophysics, black hole, etc. If you are interested, please come to me. Yeah. Enjoy the rest of your summer stay here. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Okay, so we can just end it here.